I don't want to talk about magnets for an hour, so please listen and catch this and catch it fast. Enrico, what's the last words I just said?
Fast. 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 Dang it.
So, an inductor looks like this when you draw it in a circuit. That's because, what is it? It's a coiled wire. That's what it is. It's a coiled wire. Now, here's what's interesting about an inductor. If I put an inductor opposite of a battery, what happens is fascinating, because the inductor you can't run current through a coil unless you already have a magnetic field. But there's no magnetic field. Current running through a coil makes a magnetic field. You understand the problem?
Wait, what? Say that again?
So, right, you need one to make the other and the other to make the first. And that's a problem. So when I first throw the switch, I should have a switch on here, so let me put a switch in here. So when I first throw the switch, what happens is, I close the switch, nothing happens. For a moment, for an instant, nothing happens. I have a battery and a wire. And yet, what comes out of the battery is a whole lot of, hey, there's an inductor there. I can't go through this without a magnetic field. And I can't have a magnetic field unless there's already current going through that wire. So we have a problem here. So what happens is, initially, this acts like an incredibly big resistor. And then what starts to happen? A little bit of current gets in there, which creates a magnetic field, which makes it easier for more current to get in there, which causes a more magnetic field. We need more to get in there, and then bam, we're good for a while. So far, once it gets up to full strength, once it's a full magnet, this thing does nothing. So initially it acts like a super resistor, and then it acts like a nothing resistor a short time later. Make sense?
Wait, when you say a short time, is that depending on?
It's going to depend on the time constant, which we'll get to in a little bit. But you understand this basic thing. The second thing is this, which is even more interesting. Let's say I then open that switch. I got an inductor that's fully magnetized, ready to go. And then I put another route like this here, and I close that one. What's going to happen? Well, the inductor's got current in it. It's got magnetic field stored up. It wants to keep its magnetic field. So what does it have to generate to have a magnetic field? Current and voltage, by the way, potential difference, but it's going to generate current. So what happens is it stores up, it kind of magically stores current in its secret little place that it's hiding on. The moment you open up the battery, it says, wait a second, I don't like that change either. I want to keep my magnetic field. So it'll force current into the system to keep it going, to keep its magnetic field up. Now, it's not really the way it works, but it's kind of the way it works, ideal-wise. Certainly, if you're talking about resistors, talking about circuits, this is the way you should look at the idea. What an inductor is the old man. Get off my lawn. I don't like change. He would have voted for a Republican in the last election. He is the staunch conservative. Do not like change. What are the changes? I'm resisting it. Don't care. No change. No change here. Make sense? Now, the official formula for how it resists change is this. Its voltage, its potential difference, what it's able to generate, is going to equal to L, that's the inductance, times di dt. And I'm going to throw a negative out in front because if you got current going one way, if there's a change in current going one way, which way is the voltage operating? The other way. Hey, stop it. No current this way. We're not letting that happen today. Okay? So resist change. No matter what the change is, it resists the change. This is why, by the way, every single device you guys show me and say, I've got a perpetual motion machine that works on magnets. I have to look and say, what does a magnet do? Resist change. That's all it ever does. It's a dampener. That's what it does. Consistently. Okay? All right. Now, there is one other formula, and I think I've got it right, so I'm going to write it down here. It's the energy of an inductor, which is not going to come up, but we might as well give it to you just in case they decide to. Just in case the microphones in my room cause them to think, oh, yeah, we should give it to them this year. 1/2 Li squared. Yeah. You know how sure I am? I'm looking it up right now.
Oh,
Make
so
absolutely
the
certain I
same
didn't.
as the-
Yeah, right there. So again, consistently, because as the current goes up, the amount of energy you generate goes up as 1/2 I squared, right? Because it's a triangle.
What's the unit?
Okay, so the unit for a inductor is measured in the guy who invented it, which is a guy whose last name was Henry. So we measure it in henries. I'm not kidding. Can't make that up, can you? It's a Henry. It's even worse. Almost always they capitalize that unit, which is a dumb thing to do because everything else is not capitalized. I don't understand why Henrys have to be capitalized, but they oftentimes are.
So
H, Henry.
big H.
Big H. Or little h, except little h is fine. Why change things? IUPAC says it has to be little h, but everybody else says, nah, give Henry his due.
His name.
So it doesn't.
Okay? What? Yeah, it doesn't make sense at all. It doesn't, it's not legit. Okay, so moving forward, if you take a battery and attach to an inductor, what does an inductor do?
Nothing at first?
No, reverse.
Oh, right.
It's super resistor, boy, because you're changing something. You put a battery on my lawn. Now we're gonna fight. And so it's gonna start off. You put a 100 volt battery in my face. I'm gonna give you 100 volts right back at you. And then I'm gonna get kind of used to it, and I'm gonna let a little bit of voltage through, a little current through, a little bit more, and after a while, I'm not moving the battery. You're not moving the battery. By the way, the only thing you can do now to tick me off is what? Come get the battery, take it back off my lawn. Now I'm ticked off the other way. I'm going to put a battery right back there. I'm going to run current just as if it was there.
So,
Okay?
what happened?
You take away battery, brace for this. So first, if you put a battery attached to an inductor initially, it acts like a super resistor. And then slowly but surely, or another way to look at it is it acts like a voltage source pointed the wrong way. Until you get current going through it, it doesn't want anything to do with you. Now, if you take the battery away and replace the resistor, what's it going to do? It's going to keep the current going as long as it possibly can until it runs out of gas. It's an old man.
Wait. You take away battery and fix with this.
What's going to happen? What does the inductor want? One inductor wants no change at all. So it's going to keep the voltage the same and run current through the resistor as if the battery was there. But it's going to slowly bleed off, right? It's only got so much stored. Good? All right. So then the time constant gets interesting because the time constant, the inductor works almost exactly opposite of a capacitor. So what's the time constant going to look like? Nothing that makes any sense at all. L over R. L is measured in H's. No, you shouldn't. It should be a big L. My bad. Now, I learned this upside down, so you guys have to keep an eye on me. I learned it now. My time constant is always on the top, not the bottom, so I struggle with this, but I'm going to double check. Delaware, isn't that nice? Which means L is actually on the bottom of the equation, R is actually on the top. That makes sense. That's why I don't make the big bucks. I don't understand stuff like that. Because it makes my life harder. All right, try example. Try the example. But I give you no information. But try it anyway. See if you can do it. Try the example problem. If I give it to you, you should be able to switch or first assemble everything. What happens? Enrico.
So the inductor's like, no.
No. So what's got my current as time wears on?
It's going to slowly increase.
Increase, because initially it's going to be none. So I'm going to use the increasing formula.
Yeah.
So I'm going to go I equals I max 1 minus E to the negative T tau.
I didn't think about that.
All right, so we got to think about this really hard. We got I equals, so when am I going to have the maximum current? Karis?
When
I know I don't. I'm still in the burger.
at the end. Wait, like
At the end. At some time in the dim and distant future, they usually use the phrase a long time later. A long time later, the old man's like, whatever, it's been on my lawn for a long time, I don't care anymore. Don't move it. You're not moving it, are you? Yeah. So,
Take it away.
when that happens, this is doing a whole lot of nothing, right? Just running current through it, it acts like a wire. So in that case, what's my current maximum going to be? 14 amps. 1 minus e to the negative, we want to know at 0.1 seconds, so I'll put a 0.1 up there. 0.01, sorry, 0.01. And then how do I find my time constant?
L over R.
Is L over R, which is equal to 7 over 1, which is 7, agreed? I'll put a 7 in here, and then grind it up.
0, 1, 9, 8, 5, 7, 2, 1, 1.
Good.
Yeah.
What'd you get? Oh, it's at the very beginning. Never mind, it's at the very beginning. So yeah, it's gonna be a small number. What's everybody getting? All right, one more time. Sorry.
Okay. Mr. Resney,
Yes.
I think the voltage equals L times
I don't
I
know.
over J and T, and then
Oh.
like you can put right answer. I can put it too. It's so scary.
Yeah, but that you got a solid state. You didn't get the right answer. You got the initial because it's only 0.1 seconds. If I'd done a different number, you'd be in deep trouble, I think.
Wait.
Well, how'd you do
what
it?
did you get?
Well, I did 14. All right, yeah, go L.
So 0 equals
No, I put 14. 14 equals 7.
7. The IDT.
DT, and DT is 0.01.
No.
Integral with FE, integral of 14 with respect to
Hey, but it
I
works.
is equal to
No.
integral
Yeah, it worked
of
because I picked a
7
point very
with
close to the
respect
beginning.
Okay, what if you pick a different number?
Yeah, well, it could work.
Oh, no.
The truth be told. All right, so is it good?
Yes.
Sure.
Okay, so you can do these problems.
Is there a
Do number 1.
I have a question.
Yes.
So if tau equals L over R, data R times C, can you just say L equals R
And
squared
what would
C?
you do with that
Explain
information?
it
No.
Why?
No.
Yeah, you do L over R equals R times C, and
Right,
you move the R
yeah.
over, and you get L equals R squared C.
Not linear. Yes.
What are your bounds?
Is the
So
positive,
plus C.
like when you're looking at the pictures
They
of
subtract
the,
out.
the short end, is that the positive end or the like?
No,
battery?
the longer end is positive.
Okay, so the energy flows from.
Your current flows from the big side to the other side, even though really what's happening there is going the other way. But
But your current flows from the big side
that's
to the
that's
small
what we
side.
say.
Okay, that's really what I needed to know.
That's all you need to know.
Thanks.
Unless sometimes they'll say, "Oh, a negative flow of charge." You're like, "Come on, why are you doing that to children?"
Why?
Wait, Resney, can you do like a different time? Like, can you just like say different time? Because I want to see if
Yeah, probably where it would be maximally wrong is like 7 seconds. That's probably where you're gonna run into the biggest error.
Oh, wait.